This is section 4.1, part 2. In this section, we're trying to graph polynomial functions. All right, so let's move on. Let's continue. And in the next example, we're supposed to determine whether or not these values of x, 2, and negative 5 are solutions or zeros or x-intercepts for this particular polynomial, x to the third plus x squared minus 17x plus 15. Pause the video, see if you can determine if they are solutions or not. All right, so hopefully you've determined whether they're zeros or not. And remember that zeros, by zeros we mean, let me just adjust my pen here. By zeros we mean x-intercepts as well. All right, so let me show you a couple of ways to do this. I guess we'll begin, I'll show you maybe a couple of ways. Yeah, just two forms. So method one is to evaluate. All right, so that just means that, for instance, that I gotta compute p of 2 and p of negative 5. Yeah, I want to know what this is, what these values are. If p of 2 happens to be equal to 0, then that means that 2 is an x-intercept. If p of negative 5 happens to be equal to 0, then negative 5 is an x-intercept. And I can do this by just doing some arithmetic, by replacing all of my x's with either 2 or negative 5. But I'm going to take advantage of my calculator here. I'm going to take advantage of my calculator. I'm going to use my calculator to do this. All right, so let me turn on my calculator here. Let me just kind of make it. So let me turn on my calculator. Let me erase whatever I had going on before. I'm going to go to y equals. And I'm going to clear this polynomial that I had entered. So I'm going to enter this current polynomial right now. So x to the third, x to the 3. I'm going to get away, right now my cursor is up here in the exponent. I want to come down from the exponent. So you hit this little forward button, plus we set x to the second, x to the 2, minus 17x plus 15. All right, so that's my polynomial. And right now, I guess one thing I could do is I could go look at its graph. And I can see the x-intercepts. This x-intercept over here on the left, I think happens at negative 1, 2, 3, 4, negative 5. So I think negative 5 is a 0. What about 2? Does my graph hit the x-axis at 2? 1, 2. I don't think 2 is going to be an x-intercept. So that's just based on my graph. So I think that just based on my graph, negative 5 is an x-intercept, and 2 is not an x-intercept. But if I want to be a little bit more precise, instead of looking at the graph, what I would do is I would go to a table. Up here where you have the button for graph, on the top it says table. So I'm going to hit second, table. Yeah, let me clear these values here. Let me just clear all this table. And depending, so sometimes when you actually, let me do something else here. I'll show you I'll tell you what I did here in a second. Sometimes when you open a table, it'll look like this. You see, my x's are already determined for me. My calculator is just doing 20, 21, 22, 23, and then based on those x's, they get plugged into my polynomial, and then I get the corresponding y values. If this is the case, well, I mean, you know, maybe you need to enter, I don't know, a value of x that's maybe 722. It would take me a while to scroll down all the way to 722. Yeah. So maybe instead what you want to do, see, right now the calculator is producing the x values for you automatically. I don't want the calculator to produce the x values automatically for me. I want to enter my own x values. So to do that, I can go to this little option up here above where it says window, it says table set. So second, table set. And so then right now my table is starting at the value 34. The table is counting by 1. And right now my independent variable, that's the x, it's set to automatic. And my dependent variable is set to automatic as well. The dependent variable, we're going to leave it in automatic, but the independent one, so the independent variable, I'm going to change it to ask. So then the calculator asks me, what value of x do you want to plug into your polynomial to compute a y value? That's what I want. So I'm going to change my independent setting to ask. And now let me go back to the table. And the table should just be empty at this point. And now I'm just going to enter the values of x that I'm interested in. So for instance, I want to know if 2 is a 0 of my polynomial or an x-intercept. So I'm going to hit 2, I'm going to press enter. And if my x is equal to 2, my y is -7. So p of 2 is 7. What is p of -5? If my x happens to be -5, and in order to enter -5 here, be careful, don't use this button right here. Use this one down here, that's negative. -5, my y is 0. So that means that -5 is an x-intercept. Okay, so let's, that would be the easiest way to determine if these things are zeros. So this is not an x-intercept, and this guy we decided yes. Okay, so that's method 1. That's the easiest scenario just to evaluate. Let me talk about method 2. Method 2 is a little bit more cumbersome, but if you are comfortable with this method 2, then it helps you factor. It helps you with factoring polynomials that are of degree higher than 2, a polynomial of degree 5. If you can do long division, then you are able to sort of kind of help you factor. So I'm going to use long division. All right, so let me show you how I would test. If so for instance, right now I want to know, is x equal to a 0? That's the question that we want to answer, and we want to answer it by using long division. Well, this is the same thing as asking, is x minus 2 a factor? I guess here I should have said, is x equals to a 0 of p of x? That's what I want to know. That's equivalent to saying, is x minus 2 a factor of p of x? These two questions are equivalent. All right, so then right now what I want to know is, does x minus 2 divide evenly into my polynomial? X to the third plus x squared minus 17x plus 15. Okay, so let me show you how this long division works. Perhaps you already know how to go about this long division. So right now what you're going to ask yourself, so the thing that goes up here is called the quotient. So we're going to start forming the quotient. So you got to think right now, something times x should give me x cubed. And I think that something is going to be x squared. So I put x squared right there. So x squared times x, that's x cubed. And then x squared times -2, that would be -2x squared. And then I say minus. So x to the third minus x to the third, that's 0. And then x squared minus -2x squared. So be careful with your signs, the signs there. That would say x squared plus 2x squared. Well, that's 3x squared. And then I bring down this -17x minus 17x. Okay, and now I gotta continue forming my quotient. So now something times x should give me 3x squared. And well, I think that something should be 3x. All right, so let me write down 3x up here. So I'm gonna say plus 3x, and so then I have 3x times x, that's 3x squared, and then 3x times -2, That's negative 6x. And then I have to subtract the top row minus the bottom row. So 3x squared minus 3x squared, that's 0. Negative 17x minus negative 6x. So that's saying negative 17 plus 6. That's going to be negative 11x. And then I'll bring down my 15. Okay, and then more of the same. So let me think about what's the next part of my quotient. Something times x is supposed to give me negative 11x. Well, I think that has to be negative 11. So negative 11 times x, that's negative 11x. And then negative 11 times negative 2, that would be positive 22. Okay, and then we have to subtract the top row minus the bottom row. So negative 11 minus negative 11, that's like saying negative 11 plus 11. So this becomes 0. And then 15 minus 22. 15 minus 22, that's negative 7. Okay, this value down here is called the remainder. And if my remainder happened to be 0, then that would say that x minus 2 is a factor of my polynomial, or that x equals 2 is a 0 of my polynomial. But right now my remainder is not 0, so therefore x minus 2 is not a factor. And we already knew that. The thing up here is called the quotient. And the thing to notice here is that, look, the remainder that we got here is the same thing as what we got from evaluating p of 2. Actually, let me check that with my calculator. Oh yeah, so we said that p of 2 is supposed to be negative 7. So this should be negative 7 right here. And notice that it's the same thing as the remainder that you get after long division. That is not a coincidence. That always happens. If p of 2 had been equal to 0, then my remainder would have been 0. Yeah. Again, if I was just trying to determine whether or not these things are 0 of my polynomial, I would just probably evaluate. But if I had to break down my polynomial, if I had to factor it into linear factors, then this method of long division then allows you to find all of the linear factors. All right, so let's see. So let's move on to the next thing, multiplicity. So we have that, so we're going to talk about the multiplicity of an x-intercept. Yeah, so what we're going to say is the following. So let's see, so we have the following. So if x minus c raised to the k is a factor of my polynomial p of x, and so yeah, just imagine that I have a factor. So x minus c to the k is a factor of my polynomial p of x. If this exponent k happens to be odd, then the x-intercept c comma 0, my graph crosses the x-intercept at c comma 0. If the exponent is even, then the graph is tangent to the x-axis at c comma 0. So let's see what that means. So let's kind of analyze that for a second. So to be tangent means that it touches but does not cross. That's what it means to be tangent. It just touches the x-axis but doesn't cross the x-axis. So let's see. So with even multiplicity, you touch the x-axis and bounce off of the x-axis. With odd multiplicity, you cross the x-axis. And again, the multiplicity is just the number up here, your exponent, that little k. If it's even, you touch the x-axis but do not cross. If it's odd, you cross the x-axis. Multiplicity of 1. If you had multiplicity of 1, so for instance, imagine you had a polynomial like this. P of x equals, I don't know, x minus 3. That has multiplicity 1, because I could think about it as it being x minus 3 to the 1. So that's multiplicity, odd multiplicity. And what's going to happen is that it's going to cross the x-axis. Crosses the x-axis. And if the multiplicity is odd and greater than 1, then you still cross the x-axis. All right, so let's put these ideas to work. Let's see. Let's think about this next example here. So the idea of this next example is that you're supposed to identify all of the x-intercepts. You're supposed to determine what are the multiplicities of the x-intercepts. And then draw a little sketch of the graph of this polynomial. So pause the video and try to do those things on your own. All right, good. Hopefully you got a little sketch. You know what the x-intercepts are, and you know what the multiplicities of the x-intercepts are. All right, let's begin by, let me ask a question, right? Like a more general question right now. What is the degree of f of x? What's the degree of f of x? I want to know the degree. Why do I want to know the degree? Because if the degree is even, I know what the behavior is supposed to look like. If the degree is odd, I know what its behavior is supposed to look like. So what's the degree of this polynomial f of x? And so, I mean, yeah, the degree is not going to be the highest exponent. The degree is not 3. The degree, imagine that you actually multiply this out. So you would have to begin by doing x minus 1 squared. That's going to give you something with x squared. And then you multiply that times x to the third. Well, that's x squared times x to the fifth. X squared times x to the third, that's x to the 5, and then times x, that would be x to the 6. So the degree of this polynomial is 6. Another way to think about it is that you have this. It's going to be x to the third times x squared times x. And well, what ends up happening is this becomes x to the 3 plus 2 plus 1. So x to the 6. X to the 6 would be the leading term if you were to actually multiply all of this out. So the degree of my polynomial is 6. Based on that, so I know that the degree of my polynomial is 6. And not only that, I also know that the leading coefficient is positive. So the behavior of my polynomial should, the behavior of my graph should maybe do something like this. Let me give myself a little bit more room here. So this is what I expect to see in the end. I want to see some little graph that sort of opens upward, like a U that opens upward. Right? So the first thing I had to do is determine the degree of my polynomial. I know that the degree was 6 because it's x cubed times x squared times x. And that's x to the 6th. And I know that it has a positive leading coefficient. The leading coefficient is just 1. Okay, now let's find the x-intercepts. So to find the x-intercepts, I have to set each one of the factors equal to 0. So x cubed equals 0. I have to say x minus 1 squared equals 0. I have to figure out what is x plus 4 equals 0. And from the first thing, I would conclude that x is equal to 0. From this, I can conclude that x equals 1. And from this one, I can conclude that x equals negative 4. And so then, now I can figure out what the x-intercepts are. So the x-intercept here would be 0, 0. The x-intercept here would be 1, 0. The x-intercept here would be negative 4, 0. Okay, now let's think about the multiplicities. So what's the multiplicity of 0, 0? So 0, 0 corresponds to this factor x cubed. And what's the exponent here? Well, it's odd. So this has odd multiplicity. So here the multiplicity is 3. What's the multiplicity of 1, 0? Well, 1 comma 0 corresponds to this linear factor, x minus 1 squared. And the exponent here is 2, so the multiplicity is 2. And then negative 4 comma 0. Negative 4 comma 0, this x-intercept has multiplicity. That x-intercept corresponds to this linear factor, x plus 4. And the exponent here, even though I don't see any exponent, it's supposed to be a 1. So this is multiplicity 1. So odd, even, odd. Okay, so let me see if I can sketch all it. Now I have a lot of information about my graph. I know that my graph is supposed to resemble a U that opens upward. It hits the x-axis at negative 4 comma 0, at 0 comma 0, and at 1 comma 0. And remember that if your multiplicity is odd, you cross the x-axis. If your multiplicity is even, you just touch the x-axis and bounce off of it. Yeah? So let's put all of this together. So that's negative 4 comma 0. This is 0 comma 0, the origin, and 1 comma 0. All right, let me see if I can put all of this together. I know that negative 4 comma 0 has odd multiplicity, so my graph is going to cross the x-axis. So I cross the x-axis right there. And then at 0 comma 0, my graph crosses the x-axis again because the multiplicity is odd here at 0 comma 0. So I'm going to cross the x-axis right there. So I cross the x-axis. And then at 1 comma 0, my graph just touches the x-axis. It doesn't cross. So at this x-intercept at 1 comma 0, my graph just touches and bounces off of the x-axis. So let's see if we can make that happen. Again, sorry about my sketch. It's not the best, but it captures the idea. So we're going to say this. So I just touch the x-axis and bounce off. I do not cross the x-axis there. So we said here we just crossed. And that's at negative 4. Right there at 0. At 0 we just crossed. And over here at 1, we just bounced off. And did not cross. All right, this would be this is a horrible little sketch, but it captures the general idea of the polynomial. All right, so let's move on to the next one then. Actually, you try the next two. So use the same instructions. In this next two problems, you're supposed to do the same thing. You first want to factor the polynomial as much as possible. Part B is already factored for you, but in part C, you're going to have to do the factoring yourself. And then identify the x-intercepts and their multiplicities, and create a little sketch of the graph. All right, so hopefully you've created a little sketch. You know the x-intercepts, you know the multiplicities. Let's compare some answers here. Again, I'm going to begin by determining the degree. I'm going to begin by determining the degree of p of x in this case. I want to know what is the degree of p of x. This polynomial, if I was to actually multiply this out, I would end up with something. If I was to actually multiply it out, I would end up with this negative 5x to the third. And then I might have probably some other terms. I do not know what the other terms are, but I know that if I was to multiply this out and write it in descending order, my leading term would be negative 5x to the third, because I would have to multiply x squared times x, well, that's x to the third, times negative 5. So negative 5x to the third would be my leading term. All right, so I'm dealing with an odd degree polynomial with a negative leading coefficient. That means that I expect to see, so right now my leading term is negative 5x to the third. So that tells me that my polynomial is going to do something like this. Because I'm dealing with an odd degree polynomial with a negative leading coefficient. All right, so this is what I should expect at the end, my polynomial to sort of look like. But now I gotta fill in the details of what happens here in the middle. This is just the long-term behavior. What happens as x goes to negative infinity? What happens as x goes to positive infinity? But what happens in the middle? All right, so then let's identify the x-intercepts. So let me think about my x-intercepts. I think my x-intercepts are going to be negative 2, 0. That corresponds to this factor right here, x plus 2. Well, negative 2 is what makes that part 0. And let me think about what's the multiplicity of this x-intercept. I would say that the multiplicity is 2. So this has multiplicity 2, so even. My other x-intercept is 3, 0. And it has multiplicity 1. That's odd multiplicity. And this negative 5, well, technically, yeah, it is also a factor of my polynomial. I would have to set it equal to 0, but then I would have an equation that says negative 5 equals 0, which is not true. So that really doesn't correspond to an x-intercept. So I only have two x-intercepts, one at negative 2, whose multiplicity is even, and one at 3, whose multiplicity is odd. So let me try to put all of this together. All right, so that's negative 2, 0. The other one is 3, 0. Since I have, so this left x-intercept has even multiplicity, that means that my graph just touches the x-axis, bounces off, and does not cross. So just bounce off of the x-axis at negative 2. Okay, so let's try to see that. So something like that. And I know that my graph keeps on going up towards the left and up because that's what I should expect to see from the leading term. Okay, and then my graph does something, probably goes up, and then I'm supposed to hit the x-axis again over here at 3. And since the multiplicity is odd for that x-intercept, I cross the x-axis there. Okay, so then that means I go all the way to, I don't know, probably way up here, and then I cross the x-axis right there. Sorry, it's difficult to kind of draw straight lines when you're at an angle on your computer. That's why my lines are so sketchy. So this is negative 2, and that's 3. Yeah, and I think that sort of captures the overall idea of the polynomial. This is not per se a very accurate graph, but it just kind of serves the purpose. All right, the next one, let's see. In the next one, the first thing we gotta do is factor. We gotta do some factoring. So I'm looking at this polynomial. It's of degree 4. So, well, let me just say right now, let me do my analysis over here of degree, because that always helps. So the degree here is 4. The leading coefficient, or yeah, so the leading term is negative 2x to the 4th. Negative 2x to the 4th. Which means that I'm going to have some type of polynomial that opens downward. It's like some downward facing u. I just do not know what happens in the middle. That's from my leading term test. Now let me try to factor my polynomial as much as I can. The thing to kind of think right now is you have two terms and you have to think to yourself, what's the greatest common factor of these two terms? What do they have? What's the largest thing that they have in common, these two terms? And I would say that the thing that they have in common is x cubed. So I'm going to factor out an x cubed. And if I factor out x cubed, this looks like this, negative 2x plus 3. And I would say that that is the linear factor form. That's what's supposed to go here. The linear factor form is x cubed times negative 2x plus 3. All right, so now let me use that to help me find my x-intercepts. So I'm going to set x cubed equal to 0. That would say that x equals 0, and which would imply that 0, 0 is my x-intercept, and it has multiplicity 3, which I guess is odd. Yeah, and then in order to find the other x-intercept, I would have to set the other factor, negative 2x plus 3 equals 0. Set that equal to 0, solve for x. If I solve here for x, this I would have to subtract the 3, so minus 3, and then divide by negative 2. So negative 3 divided by negative 2 is positive 3/2. Alright, so then that means that my x-intercept is 3 over 2, 0. The multiplicity is 1, which is also odd. I know that it's 1 because the exponent here is just a 1, even though it's not explicitly written there. Okay, so let me try to put all of this together. I have an x-intercept right at the origin, 0, 0. I have another x-intercept at 3/2, 0. 3/2 is 1.5. So I'll sketch it right there somewhere in the middle. So 3/2, 0. Okay, my graph is going to cross the x-axis on both points. And so then I think my polynomial looks something like this. So my graph crosses the x-axis right there. It's going to cross the x-axis over here. And yeah, that is what my polynomial, I mean, that's a horrible little sketch, but it is kind of the general idea of the polynomial here. At both places, at both x-intercepts, I had to cross the x-axis because the multiplicities were odd. All right. 2 more problems in this section. Actually, 3 more problems. Let's try them. Same idea. Same idea. You're given some polynomials, and then with these polynomials, you're gonna have to factor them, or you might have to use your calculator to find all of the factor or the linear factor form. And then once you kind of come up with a linear factor form, then sketch the graph. Identify the multiplicities of your zeros. All right, let's compare answers. Let me think about this guy right here. So I know that the leading term is 6x to the 4th. And so then that's an even degree polynomial with a positive leading coefficient. So my graph is going to look something like that, upward facing u. All right, let me try to factor this. Let me think about factoring. I know that I can factor out an x squared from everything, and this becomes 6x squared minus 13x minus 5. Yeah? And I think we can go a little bit further with this. We can say that this is x squared. And now I'm going to actually try to do factors. So this is a quadratic polynomial in this parenthesis. In this upper parenthesis in here, I have a quadratic polynomial that I want to factor into linear factors. So I'm thinking 3x and 2x probably, so that I have that 3x times 2x, that gives me 6x squared. And then let's see, now I gotta come up with something that multiplies. So yeah, something times something gives me negative 5. And I think what I'm gonna have to conclude is this. I'm gonna have to do minus 5 and plus 1. I think that'll work, because let's check. 3x times 2x, that's 6x squared. And then 3x times negative 5, that would be negative 15x. But then negative 15x plus 2x, that would give me negative 13x, which I need in this as the middle term. And then 1 times negative 5, well, that's negative 5. So I think this is my linear factor form. Okay, and so then let me think about finding my x-intercepts now. So I have this little equation in order to, that will give me the following x-intercept, 0, 0, and the multiplicity is 2. Let me set this guy equal to 0. That would say that my x-intercept would be negative 1/3, 0, and that has multiplicity 1. I would have to do 2x minus 5 equals 0. That would say that my x-intercept is 5/2, 0, and it's also multiplicity 1. So negative 1/3, 0, 5/2, 0. Remember, if the multiplicity is even, you touch the x-axis and bounce off. If the multiplicity is odd, then you cross the x-axis. So let's try to put all of this together now. Okay, let's see. I'm gonna pretend that that is right there. That is 0, 0. I'm going to say negative 1/3. I'm gonna put it right there. So that's supposed to be negative 1/3. That's supposed to be 0. And then 5/2, we'll put it somewhere over here. We'll say that this is 5/2. Actually, no. Let's put it even further out. Let's put it even further out. So let's say that 5/2. We'll put it right there. That's 5/2. Okay. Since we have a polynomial of degree 4 with a positive leading coefficient, we're supposed to expect an upward opening u. So let's see if we can make all of this happen. So I begin there. I know that I cross the x-axis at negative 1/3. At negative 1/3, my graph crosses the x-axis because I have odd multiplicity. And then at 0, 0, I just touch the x-axis. So my polynomial probably goes down here. Sorry, I bunched it up and it's kind of difficult to kind of sketch, but let me do my best here. So my polynomial goes down. It touches the x-axis at the origin, but then it bounces off. So it just touches the x-axis at the origin and it bounces off. And then it does something down here and it crosses the x-axis at 5/2 because 5/2, 0 has multiplicity 1. So I cross the x-axis at negative 1/3. I just bounced off of the x-axis at 0 and I cross the x-axis at 5/2. Again, this is probably a very ugly little sketch, but this is what's going on with my polynomial. Alright, last little graph. This guy right here. This one's maybe a little bit more challenging. I mean, especially in trying to factor. In the previous things where we had to factor, in the previous polynomials where we had to factor, all of the terms had something in common. I'm looking at this part E, and that I have 4 terms. There are 4 terms in my polynomial, and there's nothing that they all have in common. I don't think there's something that they all have in common. So how can I proceed here? What can I possibly do here? And well, maybe long division would sort of help out in this situation. There's also what's called the rational zeros test. There is this test that, depending on whether or not you've been exposed to it, you can sort of generate some guesses for what are the x-intercepts. And the guesses have to do, the guesses are fractions. The fractions are made up, so the numerators of these fractions are numbers that divide 8. The denominators are numbers that divide 1. So you create these fractions by thinking of the factors of the constant term in the numerator and the factors of the constant term in the denominator. It's called the rational zeros test. I'm not going to use it just because it's cumbersome. What I'm going to do right now in order to try to figure out the linear factors of this polynomial is I'm going to use my calculator. I'm going to enter my polynomial into my calculator. So let's see, let me clear this. I'm going to say x to the third. Alright, x to the third minus 3x to the second Okay, minus 6x plus 8. All right, so that's my polynomial. I'm gonna look at its graph. And now I'm just based on the graph, I'm gonna try to guess what are the x-intercepts. That's what I'm gonna do. So right now, I think that the x-intercepts are at -2. There's probably an x-intercept at 1. And there's an x-intercept at 4. That's what I think. I think that's what are those are my x-intercepts. So let me think about the x-intercepts. And again, right now it's just I'm using my calculator to look at the graph of my polynomial, and based on the graph, I'm just guessing. Because my graph is also not that accurate. I mean, in terms of pictures, the little graphs are a little kind of weird. So I think that at x equals -2, at x equals 1, and at x equals 4, that's where I have x-intercepts. Let me write that down. X equals -2, x equals, we said 1 and 4. X equals 1 and x equals 4. Now to be sure that, to be sure that x equals -2 is an x-intercept, what we could do is use our table. I could go to second table, and I am going to enter for my x value -2. So -2, let me hit enter there. It is an x-intercept because my y value is 0. Let me check to see if x equals 1 is an x-intercept. So if my x is equal to 1, my y is 0, so that's good. Let me enter 4. If my x is equal to 4, my y is 0. So these are x-intercepts. We used our calculator in this case to find them. And if x, if this x equals -2, if that's an x-intercept, that means that x plus 2 is a linear factor. X equals 1 would mean that x minus 1 is a linear factor, and the fact that 4 is an x-intercept would mean that x minus 4 is a linear factor. So then the factorization of my polynomial turns out is x plus 2 times x minus 1 times x minus 4. So by knowing the x-intercepts, in a sense, you know the linear factors. They are the same thing. And I know that they all have an exponent of 1. Why is that? Well, because my polynomial is of degree 3. And so then if I had any exponents bigger than 1 here, I would end up with a polynomial different than one of degree 3. All right, so the x-intercepts mean that, well, I have the following x-intercepts: -2, 0, 1, 0, 4, 0. They all have multiplicity 1. They all have odd multiplicity. So then that means that my polynomial crosses the x-axis at every x-intercept. Also, I should just know that my polynomial right now in the long term would behave something like this. Why? Because my polynomial is of odd degree. And by the way, do not confuse the degree of a polynomial with the multiplicity of an x-intercept. Even though the degree could be odd, that's talking about something totally different than odd multiplicity of an x-intercept. So this is the long-term behavior of my polynomial, and I know that it hits the x-axis at -2, at 1, and at 4. So let's put all of that information together. So -2, at 1, and at 4. All right, so I think something like this, something like that. Oops. Let me make this a little bit nicer. There we go. And notice that I cross the x-axis at every x-intercept because all of the multiplicities are odd. So at -2, I cross the x-axis. At 1, 0, I cross the x-axis. And at 4, 0, I cross the x-axis. This is not a very accurate sketch, but it does capture the behavior of the polynomial. Okay, last question in this section. Let's read it. I'll give you a second to try it on your own, and then let's try to answer this together. So there are x teams in some sports league, all teams play each other twice. A total of n of x games are played, where n of x is x squared minus x. Okay, a softball league has 9 teams, each of which plays the others twice, so the same rules. If the league pays $110 per game for the field and umpires, how much will it cost to play the entire schedule? Oh, sports. I'm really bad at them. So pause the video, see if you can answer this question. Alright, so let's see. So n of x represents the total games played. And it's the total games played, and the x represents the number of teams. So the more teams, the more games played. The less teams, I would suppose the less games played. Something like that, I don't know. Right now my x is 9. So I need to know how many games are going to be played by a league that has 9 teams. So the first thing I'm going to have to figure out is what's n of 9. Well, I guess in this case it's going to be 9 squared minus 9. So that's 81 minus 9, which I guess would be 72. Yeah, so a league with 9 teams plays 72 games. Alright, and now they told me that each league has to pay $110 per game for the field and umpires. So I guess we're gonna have to we're gonna play 72 games, and for each game we have to pay $110 to the field and the umpires. So let's figure this out. 72 times 110, that gives us 7,920. So 7,900, and I guess we're dealing with dollars now. 7,920. This is a polynomial of degree 2. We didn't really need to know its graph, but whatever, just a little bit of practice with polynomials. Alright, so that is it for this section. Thank you, and I'll see you in section 4.2.